Hello and welcome. My name is Lennart Gradiska, and in this video I want to summarize my master thesis on the design and evaluation of an integrated 3D navigation and control system for a CubeSat demonstrator. Throughout my research, I defined system requirements, designed and implemented a navigation and control system, and conducted various tests to evaluate the system performance. This video will walk you through some key aspects of my work from the initial concept to the final results. However, as I only want to give a brief summary here, it's not possible to go into detail on all aspects. If you are interested, you can download my master thesis in the video description below. Before I start with a presentation on the navigation system, I would like to briefly introduce the CADOS project in which I conducted my research. CADOS is a student's project carried out at the Aerospace Engineering Department at the FH Aachen under the direction of Professor Markus Czupalla. CADOS stands for Kaltgas angetriebener Demonstrator mit Onboard-Steuerung or Cold Gas-Driven Demonstrator with Onboard Control. The aim of the project is to develop a platform to facilitate the design and safe evaluation of subsystems for CubeSats, such as the navigation and control system. Within this work, the navigation and control system for the demonstrator will be designed, integrated, and finally tested. This page shows important design requirements for the navigation and control system. Now let's talk about the design of the navigation system. The designed navigation system consists of two types of sensors. On the one hand, an inertial navigation system, or in short INS, is used, which is based on the integration of acceleration and rotation rate measurements by an IMU. The IMU of the INS provides high frequency but relative measurements that are subjected to the influence of drift. In addition, a camera system is used, which provides less frequent but absolute position and attitude information by detecting so-called artificial fiducial markers. The two data streams are then fused within a Kalman filter. For this purpose, two extended Kalman filters with aerostate were developed, one for the position and velocity, the other for the attitude. By including the additional aerostate in the filter, errors such as non-white noise and drifts can be addressed, which a normal Kalman filter cannot take into account. To illustrate this, the so-called propagation equation, which is calculated during the prediction step, is listed here. The terms A offset and omega offset represent the error terms in the state. Now I would like to address the hardware utilized in the system. This table shows the hardware components as well as their connection to each other. To explain the distribution of tasks for each component, I've added a flow chart showing which component performs which tasks. Here you can see the integration of hardware components in the demonstrator. Care was taken to ensure that all cameras look in different directions so that at least one camera should always be able to recognize markers regardless of the orientation and position of the demonstrator. Now we come to the validation and testing of the navigation system. First of all, it should be clarified what the aim of the test series is. On the one hand, of course, the performance is to be analyzed with a focus on accuracy and robustness. In addition, the test series also aims to evaluate the specific requirements of the navigation system. To evaluate the performance, the navigation system was compared with a very accurate motion capture system. Here you can see the test setup. On the walls, you can see the artificial markers that are used as reference points by the navigation system. On the right, you can see a wooden box in which all components of the navigation system were installed to have an easier handling during testing. Now we come to the procedure of the test series. A total of 4 test series were carried out, some of which were run several times or in different configurations. The individual test series are listed here. I don't want to go into more detail about the individual tests here, but I would like to take a closer look at one of the tests as a representative. For this, I decided to use the ramp test in translation and rotation, in which uniaxial linear movements are carried out at constant speeds. Here you can see the movement graphically. First for the rotational movement, which corresponds to a rotation around the global z-axis. The translational movement was tested separately by moving the demonstrator in the direction of the global y-axis. Now we come to the results of the rotational ramp movement. On the left side of the graph you can see the movement, in this case around the rotational z-axis, expressed as a tau Euler angle. The blue line shows the results for the navigation system, and the orange line for the motion capture system. The ramp was performed at a speed of about 15 degrees per second. On the right hand side you can see the difference between the navigation and motion capture system, which is to be interpreted here as an error. In the upper plot you can see the errors in the attitude and below the errors in the position. Well, what can we see in the plots? Firstly, it's clear to see that the navigation system was able to recognize the movement and followed it. The errors in the attitude during the movement, as well as before and after, are far less than 1 degree. The calculated position is also subjected to errors, most of which are in the range of 5 mm, but can also increase to a maximum of 18 mm in short term. However, both errors are far below the limits described by the requirements. Now we come to the results of the translational ramp test. On the right-hand side, we again see the errors in position and attitude, and on the left-hand side, we see the ramp movement performed in the y-axis. The ramp was carried out at a speed of roughly 80 mm per second. Here too, it's clear to see that the navigation system was able to follow the movement, even if the errors in the position are greater than during the previous test. The errors in the position are on average in the range of 10 mm and peak briefly up to 30 mm. The errors in the position are again well below 1 degree. Of course, not only the graphs were looked at during the various tests, but a quantitative analysis was also carried out. For this purpose, 3 values were looked at more closely, which are the mean error, the error standard deviation, also often called root mean square error, as well as the maximum error, which is needed to evaluate the accuracy requirements. The results for the attitude of all test series are summarized here. The results for the position are summarized here. In summary, it can be said that the system was able to successfully calculate the position and attitude, and that errors are well below the guidelines formulated in the requirements. Particularly good results can be seen in the attitude. The results also indicate that some of the measurements errors can be attributed to inaccuracies in the setup, and the actual performance may even be better. Let us now continue with the development of the control system. While the navigation system was given a free hand in the design, the actuators for the control system are already predefined. These are cold gas nozzles with on-off switching valves. These actuators cannot generate variable forces, but can only be switched on or off. This behavior is fundamentally nonlinear and requires the use of special control algorithms. Within this work, the 2 modulator types bang-bang and PWM or pulse width modulation were examined, and controllers based on these techniques were designed. On this page, I've listed the block diagrams of the two modulator types, as well as their mathematical relationships. Both modulator types can be combined with a controller, such as a simple PD controller. This has the advantage that the system response can be designed according to the designer's needs. Now let's move on to the validation and testing of the controllers using the demonstrator itself. Since testing in a 3D environment is currently not possible, as we would need zero gravity for this, tests can only be carried out in 2 dimensions. In this picture you can see the 2D test environment, which consists of a glass plate on which the demonstrator can glide by using a specifically designed interface for this purpose. In order to test the performance of the 2 controllers, a total of 4 test series were carried out, which are presented here as a flowchart. At this point, I only want to talk about the test cases 3 and 4, the so-called maneuver tests for the PWM and bang-bang controllers. Let's move on to the execution of this test. The test consists of 3 consecutive setpoint changes. The motion to be executed by the demonstrator is shown in this shortened video. Now we come to the results of the maneuver test. First, let's talk about the PWM controller. The 3 graphs show the error between the setpoint and the measured pose. The upper plot shows the errors in the X position below the Y position, and at the bottom the errors in the rotation. The yellow line shows the results of the simulation, blue the results from the real tests, and red should be ignored at this point. As you can see, the deviation is large at the beginning of the test as the demonstrator is far away from its target pose, but then quickly becomes smaller as it gets closer and closer to the target pose. It then reaches it and is able to hold it. The 2 tables on the left illustrate the mean and max errors for the position and attitude during steady states. If we now look at test case 4, the maneuver with the bang-bang controller, a similar picture emerges. This controller was also able to reach the target pose and hold the demonstrator there. However, if we compare the errors with each other, we can see that the bang-bang controller has considerably larger steady-state errors between the target and actual position, while comparable results are visible in the attitude, which indicates that both controllers have a similar performance here. To underline the results, both test series, that of the PWM and the bang-bang controller, are compared directly here with each other. To summarize the results, both controllers show similar behavior in terms of approach rates and error reduction. However, there are some differences. Overall, the bang-bang controller shows more oscillations and a larger error range in the steady-state position. At this point, I would like to show a video of the maneuver test for the PWM controller. Thank you for watching. As Henry Petrosky said, science is about knowing and engineering is about doing. If you found this video helpful, leave a like, and if you have any questions, drop them in the comments. I'll do my best to answer them.